In this lecture, I will talk about incompletely specified functions. Incompletely specified functions, or we can call them don't care conditions. Don't care conditions. Okay, let's assume we have a function f of a, b, and c. This function has three variables, so 8 possible combination of the input can included in the truth table. In digital systems, it often happens that certain input conditions can never occur. For example, if we say a, b, and c can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These all are 8 different possible combination of the inputs. But in some systems, some of these inputs cannot occur, so we cannot have, for example, this combination. So if any combination, any condition can't occur, we don't care about those combination of the inputs. So we don't care if they are in the function since they wouldn't occur, so we don't care about them. So for example, we say if A is 0, B is 0, C is 0, it's just an example. The output is 1, 0, 1, 0. But this combination, because it cannot be occur, we say we don't care what is the what is the output of this combination, because this combination it's not possible to be happen, and the other functions which are possible, they have their own output. So we call these conditions as don't care. We show don't cares with capital D, lowercase d, or x. Okay, so let me write the definitions, and then we can start to see some examples. So we can say in digital systems, it's often it often happens that certain input conditions can never occur. Okay, we don't care if they are in the function since they wouldn't occur. Okay, so these these min terms which we have here, let's say this min term or max terms. Here the min term is min term is a, b, c, and max term is a bar plus b plus c. These min term max terms are called don't care min term max terms. These excluded min term or max terms are called don't care min term or max term. Okay, so that we call them like don't care. What about K-map? if we have these conditions in the K-map, what should we do? Like in the regarding the grouping min terms or max terms, grouping ones or zeros, because these don't cares in fact can we don't care if there are 0 or 1. We say that these don't cares like can be grouped with other min terms to form a larger group. So if we need like 1 to build a larger group, we consider them as 1. If we need 0 to build larger group of max term, we consider them as 0. So depending of our group size, we can consider these donkers as 0 or 1. So we can say in grouping, we consider them the in grouping of donkers, we consider them as 1 or 0 to build larger groups. Okay, so if we are grouping 1, we can consider them as 1 depending to the like to their locations. To have larger groups, if we grouping zeros, we can consider some of them zeros to build a like larger group of 0. One thing, if we have five donkers, we don't have to consider all of them as 1 or as 0. We can consider as many we need as 1 and as many we need as 0. Okay, so because they can get any value. Let's see one example. Here we have an example. We have two variables, x1 and x2. These two variables like control two interlock switches. So they control two interlock switches. But um, both the switches cannot be closed at the same time. So both of them cannot be closed at the same time. So we have three possible states. So we have three possible states. Those states are x1, x2, are 0, 0, 1, 0, and 0, 1. Okay, because both of them cannot like close at the same time. So we see that 1, 1 is guaranteed like to not to occur. It's guaranteed not to occur. So we say x1, x2 is equal to 1, 1 is don't care condition. Okay, so as 1, 1 cannot occur, we call this combination as like don't care. Okay, and now we want to see how we can use these don't care conditions to simplify or our like K map in the best condition, or in the like minimum to design the minimum cost function. Let's see one example. So here we have an example. We want to simplify. We want to simplify this function. F of x1, x2, x3, and x4 is equal to the sum of min terms number 2, 4, 5, 6, and 10 plus don't care for the min terms 12, 13, 14, and 15. Okay, so we want to simplify this function in two different methods. So we want to design minimum cost sum of product and minimum cost product of sum. First, let's design minimum cost sum of product together. So part A, minimum cost sum of product. Let's draw our K map. So here is the K map. Okay, A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. We feel like min terms. If we fill these min terms place these min terms in the table, we will have 1, 1, 1, 1, and 1. Let's just add donkers. Donkers is here, D, 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 and D. The rest are 0. So 0, 0, 0, 0, 0, 0, 0. Okay, now we want to simplify this function by grouping minterms. If we look to this circuit, we see that we have two ones here and one here. Of course, we have the option to group this one with this one, but why shouldn't we consider this donker? Let me undo my. Give me a second. Okay, let me draw this table again. Here is the table, and the values in the table was D and 1. Okay, so here we we have a better optimization if we can have four ones in a group, but one of them is D. Because it is D, we can consider it as 1, because as I mentioned, it's a donker, and group these four together. The next one, we have two ones in this location. Instead of grouping these two ones together, we group them with these two donkers to make a larger group. So this donker can consider as 1, the other donker is considered as 1, and finally this donker which is not in any of these groups can be considered as 0. We don't need to consider it as 1. So now we have two groups, and we write the function the red group. Both A and B are changing for all the minterms, and C is 1 and D is 0, so we say CD bar, not CD bar, because the problem is x1, x2, x3, x4. Let's change A, B, C, D to x1, x2, x3, and x4. So we have x1, x2, x3, x4. Okay, so a function is for the red group, we will have x3, x4 bar, plus for the green group, we see that x1 is changing, x2 is 1 for all cells, so it's x2, x3 is constant, it's 0 for all cells, so we say x3 bar, and x4 is changing, so it's cancelled. So the minimized function is x3 x4 bar plus x2 x3 bar. Let's solve the part B of this example. So this time we have the same table. x1, x2, x3, x4, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0 1 D 0 0 1 D 0 0 0 D 0 1 1 D 1. Okay, because part B, we want to find the minimum cost product of sum for this circuit. We need to group zeros. So in order to group zeros, we can group these two zeros with these two zeros together, and we can group these four zeros together. So as you see here, we considered this d as 0, the other d's as 1. Okay, now that we have these groups, we need to write the function. So the function will be equal to, function is equal to, for the green one, x1 and x2 is changing for these variables, so they cancel each other. x3, x4, so they should be x3 bar plus x4 bar times the red one. The red one, if you look to the red one, we see that x1 is changing, x2 is 0, so we consider x2 plus, and x3 is 0, but x4 is changing, so we consider x3. So this one is the simplified version of minimum cost product of sum. Okay, so now we are going to show one example which we design a circuit by considering the concept of tone curve. So here is the design example. Design example. Design a logic circuit to show round-off for a 4-bit BCD. We know what is BCD. Input is BCD for decimals 0 up to 9. Output is equal to 1 if input is if input is 5 to 9 and 0 is 0 otherwise. So we want to design a circuit which gets the BCD inputs for 0 to 9. The output is 1 if the BCD is equal to 5 to 9, and the output is 0 otherwise. Okay, let's design this circuit. The first thing we need to draw the truth table. So decimal value is here. BCD value is here, and output is here. BCD, of course, has 4 variables, and output is the function. Decimal numbers start from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the rest of them are unused bit combinations, because for BCDs we consider the combinations of these 4 bits from 0 to 9. Okay, so let's see. We have 0000, 0010, 0011, 0100, 0101, 0110, 0111, 1000, 1001. These are for the logics from 0 to 9. The rest of possible inputs that never occur are 0010, 00, sorry, 1011, 1100, 1101, 1110, and finally 1111. So these last combinations are not going to occur. So the now for the outputs, we say for the inputs from 5 to 9, the output is equal to 1. So from 5 to 9, outputs are 1. From 0 to 4, outputs are 0. And from for these unused combinations, the output is don't care. Okay, so if you look here, we see that from 0 to 4 we have output of 0 based on definition in the problem. From 5 to 9 the output is equal to 1, and from 1010, which is here, the output is don't care. Okay, we replace it with D. Now we want to design this circuit, so we need to draw to table the K map. So here is the K map. We have A, B, C, D. Zero 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 one 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 zero 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 one 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 zero. Let's fill the table with this information. We will have D1, D11, 1D, D1, D, D. They like the empty cells that you see in the table, in fact, are zeros. Okay, so I placed ones and these, so we have these functions. Before just simplifying this function, I want to write this truth table in the form of a minterm. So if I write this truth table in the form of minterm, we can say f of a, b, c, d is equal to sigma of minterms 5, 6, 7, 8, and 9 plus don't care 10, 11, 12, 13, 14, and 15. Okay, so we say these minterms which are from this part of the circuits, these don't cares are for this part of the circuits. Okay, so now that we have everything ready and put in the table, we need to group the cells to simplify the functions. The largest group of 1, let's first consider this group. So let's consider these ones and don't cares as a single group. Okay, 8 cells, 2 to the power of 3. The next one, the second group, we should consider these 4 cells together. Okay, and finally we can consider these 4 cells together. So this one is the best way that we can cover all ones with minimum number of groups and the largest size for each group. Okay, and we write the function. So f is equal to, for the black one, black group, of course a is changing, b is constant, so it's b, uh, and bd plus. For the green one, a is again changing, b is constant, bc, okay, plus. For the red one, if you look, we see that A is 1, B is changing, so we have A, C and D is changing, so no C, no D, and this is the final answer. So this one is the simplest possible circuit to implement this function. Okay. We have one more design example. As so let's do that together. We have second design example, design example 2. Okay, the problem is here. It says that v1 to design a self-test circuit with failure indicator as shown in the following diagram. Okay, here is the diagram. We have self-test circuit which has three outputs: output A, output B, output C. These outputs enter to a failure indicator circuit, and output is here. So how does it work? Uh, for self-test systems, we say if this has failure, then A, B, C is equal to 0, 0, 0 or 0, 0, 1. If no failure, then A, B, C is equal to 0, 1, 1 or 1, 1, 1. So these ORs in fact are not OR gates. They are word OR. No other output is possible. Okay. This failure indicator says if failure, then F is 1. If no failure, then F is 0. And now we want to design this circuit. Okay, so this circuit says that if this self-test circuit has any failure, the output will be 000 or 001. If there is no failure on this circuit, the output is 011 or 111. No like other output is possible, and this failure indicator says that if failure occurs, output is 1. If no failure, output is 0. Okay, so because we have three inputs, we need to mm, write the function. We say f of a, b, c is equal to sigma of m 01 plus donker 2, 4, 5, 6, like when the function is 1. So when there is failure, if there is a failure, we know that the output of this circuit is 00 or 001, which is min term 01, and min term 3 and 7 are not like part of these min terms because it's when there is no failure, and the other combinations are donker. So let me show you with arrows. So here we can say that these min terms are because there was an error, and these donkers are these other conditions that cannot be occurred. Okay, and now we need to design the circuit. The circuit is a K map with three variables, variable A, B, C, 0001111001. Let's fill the table 1 D D D D and 00. Okay, and this one is like the circuit, and we can simplify this circuit based on our need, so we can consider these ones together to simplify the function. Okay, that was the lecture for don't care circuits.